Okay, welcome back everyone. So let's quickly continue our video on operations on Dedekind cuts. In other words, let us now define negative a, where a is a subset of the rational numbers, and it's a cut, Dedekind cut. So we define it as such. Negative a is defined to be all x in the rational numbers, such that there exists a y that's not an a, where y is less than negative x. Okay, so first, well, it's pretty easy to show that it's non-empty. Simply take x to be negative y plus 1. So that tells us that negative x, oh, that looks like a negative sign. That tells us that negative x is y minus 1. And, oh, sorry, that's wrong. It should have been, my bad. We want y plus 1, so negative y minus 1, so that we get negative x is y plus 1, right? And, well, therefore we have clearly found an x such that, well, x is in negative a. Therefore, negative a is definitely non-empty. Okay, well, let's see. Next, we want to show that it doesn't take up the entirety of Q. And to do that, we can show a special case for this. In other words, we would like to show that a sub n, which we showed was a Dedekind cut in our first video on Dedekind cuts. And let me just remind you of the definition. It's all x in the rational numbers such that x is strictly less than n. Okay, so we wish to show that in this special case, negative a of n does not take up the entirety of the rational numbers, and that will suffice to say that in general, negative a, well, that's disproving a special case for this. It gives a counterexample. So, okay, so negative a, let's see. So we want to find z in the rational numbers such that, well, if we negate the statement such that for all y not in a of n in this case, y is greater than or equal to negative z, right? Okay, well, just take z to be equal to negative n, so that y is less than or equal to n. Well, why? Well, just notice that we showed in the previous video that for given any Dedekind cut, how should I say this? Well, I guess in our case, it is important to note that since y is greater than or equal to n, it is clearly an upper bound for a sub n, right? It's an upper bound. But we showed that if it's an upper bound, then it's for a sub n, and this actually applies in general. It's also not. It therefore is not in a. Okay, a sub n in this case, right? So this checks out. We found z such that we have found a z that's, well, not a negative a sub n. So that's what I'm trying to say. Okay. So that's what we have. So that's the first part that we want to show. Okay. This whiteboard is a bit flimsy. Next. So second part, I'm just going to quickly define z to be x minus y over 2. Okay, this is going to help us out. And we actually want to show that z prime, given any z in negative a, z prime is always greater than that, and also, well, we want to show that, of course, z prime is in fact in negative a. So maybe it's first good to show that it's in negative a. Well, let's see. To do so, how do we do that? Okay. Okay, well, let's see, so, okay, x minus y over 2, if we just consider the following, so in other words, to show that z prime is in negative a, we need to show that there exists some y, okay, well, let's consider negative z prime. So that's going to be y minus x over 2. So that's negative z prime. We want to find a y such that, yeah, exactly this. Okay, so y, I guess this isn't that rigorous because I didn't really define these earlier, but this is just a video, so yeah. Okay, well, we're going to do a chain of if and only if statements. Normally, if you were to do a normal proof, you would use this as scratch work. So start with this statement as scratch work, and then go to like a true statement, and now you've verified this. But then in the proof, you just want to revert all the steps you took, so that looks more concrete. But this is fine as well since it's just a video. Well, we have 2y less than y minus x. If and only if x is less than negative y, if and only if negative x is greater than y. Okay, and that checks out. So therefore, you can revert all of these steps are reversible. Okay, and therefore z prime is in negative a. And now let's show that z prime is in fact greater than z. Actually, in this case we're using x, right? I don't know why I used z prime then. Okay, that's fine. So get rid of the prime, I guess. So again, chain of if and only if statements. If and only if 2x less than x minus y. If and only if x is less than negative y. If and only if negative x is greater than y. Again, that checks out. In other words, the second property holds. Okay, final property. This one takes the least amount of time. We are almost done. And then after we deal with these Dedekind cuts, we'll be able to quickly get some really nice results. For example, after we prove the law of trichotomy, then we'll be able to very quickly prove the density of Q and R. So, like in 2 lines or so. Okay, finally, third property. Take is an okay word. Q less than P. P is in negative A. So if P is in negative A, then there exists a Y. I'll just leave all that writing out. There exists a Y such that Y is less than negative P. So Y is less than negative P. But notice that if we can rewrite this as Q is greater than negative P. So therefore we have negative Q here in this chain of inequalities. That just implies that Y is less than negative Q. So that checks out, right? That tells us that Q is also in negative A. Okay, so that completes this video. I'll see you in the next video where we prove the law of trichotomy. Okay? See you there. Oh, I keep forgetting to do this. QED, quod erat demonstrantum.